bonus example video. So here we're talking about radium-226. Again, this is a radioactive isotope of the element radium, and it's sometimes used in cancer radiotherapy. So let's say that we have P of T grams of this element remaining after T years. There's this relationship, this differential equation, just like the first video. And we have an initial condition, just like the first video. That first video really just does the whole section, right? And the question is going to be find P of T. There's a bunch of questions I'm going to ask you about here. We're just going to use that theorem at the beginning of the section in that first video, right? This is like our y right here. Y is equal to K times, sorry, Y prime equals K times Y. Okay, so we just use that theorem and say, okay, so P of T is equal to the initial amount, which is 12. Again, our initial amount is 12, times e to the negative lambda times t. So it's a combination of everything from this section. You can do it in a couple steps using the theorem. You can do it in one step using what we talked about in the last video and the third video for this section. Whatever you do, make sure that your exponent's negative. All right. Otherwise, if the exponent's not negative, the radium-226 is growing. And we don't want that, especially if it's being put in our bodies. Do not want radioactive substances to have exponential growth within our bodies. That would, well, it would take care of the cancer. That's probably not appropriate to joke about on stream in a video. Let's move on. Part B. What was the initial amount? What if I just say really inappropriate random things in the videos just to see if you're watching? If I get some messages saying, Jason, why are you talking about this? I'll go, oh, this person's watching the videos. Excellent, good work. All right, so again, initial amount has to do with the initial condition. Initial condition says, originally, when t was equal to 0, we had 12 somethings. Okay, what are our units? How much 12? Do we have 12 kilograms of strontium, of radium-226? Hopefully not. P of T is in grams. So initially there were 12 grams. Okay. Initially 12 grams of radium-226. All right. That's all there is to part B. Part C, what's the decay constant? That's not how you spell decay. Nice try. So again, decay constant is just the number next to the P of T. And different books have different tendencies, whether they allow the decay constant to be negative. Here, we have e to the negative lambda t. So lambda should be a positive number, and then the negative is before the lambda. The decay constant lambda is equal to 0.00043. I won't take off points, though, if you include the negative, because different texts really are kind of inconsistent about whether we call this positive or negative. But technically, according to this book, our decay constant will be a positive number. Again, the lambda is just the constant up here in this exponent. All right, let's do part D. We're really zooming through this example. Part D is how much will remain after 943 years. And this is where this problem gets really funny to me, right? Is because it phrases the question, this problem number 36 from the book. It phrases the question like, oh yeah, this is used in cancer therapy. And it's like, okay, how much is left after 943 years? It's like, I'm not going to be left after 943 years, right? But let's just do the problem. Okay. We just plug in, right? This is our t value. We're just going to find out, okay, what is p after 943? And we just plug it in. We started with 12. We still have that same decay constant as before. We're plugging in T is 943. And let's go plug it in and see what happens. So again, there's a lot of different ways that you can use a calculator. I like to use Desmos. Desmos.com is the website. But there's a lot of great ways of doing this. Negative 0.00043 times 943. Oh, almost perfectly about 8 grams. Okay. It's about 8. So we started off with 12 grams of radium-226, and after 900 years, we're now down to 8 grams. Yeah, kind of silly. But that's how we use it. Party. How fast is the sample disintegrating when 1 grams remains? Okay. This would have been faster if I just wrote it out. How fast, Party, how fast is the sample disintegrating when 1 gram remains? So right off the bat, how fast? How fast, that means derivative, rate of change. Identify that right there. How fast? Derivative. Very important thing to see. Okay. How fast is it changing when 1 gram remains? So we could find the derivative here, or we could go back to the differential equation, not the differential equation. Remember that P prime of T was equal to negative lambda T. Oh, negative lambda times P. So we're looking for how fast is it decaying. This is what we're looking for. When 1 gram remains, that's that. Let's use a different color for that. We're actually almost done. I haven't been using yellow a lot. Oh, because yellow really looks bad on the notes. So we're almost done, right? It's just negative lambda, so negative 0.00043 times P, which is 1. Oh, that's how fast. Okay. That's not very fast. Okay, so how much is that? Well, it's negative, so it's decaying by 0.00043 grams every year. So it's not decaying very quickly at this point. And remember, radioactive decay, it's exponential decay. Exponential decay is this form, right? So when there's a lot, it's decaying kind of quickly. But over time, it decays slower and slower. And when we started with 12 grams. When there's only 1 gram remaining, it's going to take a long time. It is decaying pretty slowly. So remember, the slope being negative means it's decaying. So we don't have to include the negative our answer here. All right. Oh, looks like the other cat has decided. This whole video session today has had so many cats, but usually between the videos. But now she's popping up and nope, you're not going to try to dig through my chair. We're good. Let's do the last part of this problem. Part F. F as in the letter grade furthest from what you will end the semester with. How about that? So the half-life. That's not how you spell that. The half-life of radium-226. Fun fact, this is how you actually write that radioactive isotope. The element sign, and then like a sort of backwards superscript. Anyway, is about 1,612 years. The question is, how much is left after 1,612 years? Follow-up question, what about 3,224 years? This just really wants you to know and understand what a half-life is. Remember, doubling time. How long does it take till it doubles? Tripling time. How long does it take till it triples? Half-life. How long does it take until it halves? So if the half-life is this long, how much is left after that long? Half. So after 16, 12 years, 1/2 of the original amount, 6 grams. 32, 24 years. That's another half-life. Another half-life means another half decays. So the next answer is going to be 3 grams. And then after another half-life, 1.5 grams. After another half-life, 0.75 grams, etc. So remember that comment I made earlier, right? It starts decaying slower and slower as time goes on. Which is why when there's only 1 gram remaining, it really is decaying at a very snail's pace. All right, you should be ready to, I can take off the glove. You can see my hand, my actual hand. Should be ready to take on this whole section. Good luck, and don't hesitate to let me know if you have any questions.